So, good evening. Today, what we are going to uh, do is like we are going to see selected problems from the ISI subjective and objective papers, the algebra section. Uh, so, in this session, what we are going to see is that I mean there are problems which do not require too much uh, too much background. Okay, so simplistic problems, but they have been given in a twisted manner. So let's start with uh, and probably we will have this session for 35 to 40 minutes. You can list down queries in the comment section. After I finish uh, my presentation, I will address those queries one by one. Okay, fine. So let's take so ISI M.Math subjective papers, subjective questions. So the first question that we have here, the first question is this. Let me write down the question. So the first question tells us that let M belongs to M and R. M belongs to, so I'm kind of writing M and R instead of their original question, that is an n cross n real matrix, a real n cross n matrix with all diagonal entries equals to R, with all diagonal entries equals to R, and all the non-diagonal entries are equals to S. Entries are equals to S. Okay, so then we have to compute the determinant of M. So we need to compute determinant of M. Now, now since it's an n cross n matrix, what you practically have if you write down your matrix is like this: R, R, and it goes on diagonally till R, and S everywhere else. Okay, so that's exactly the way this matrix looks. All right. Now, to solve this question, you practically need a +2 level intuition and a basic college level knowledge. Okay. So, what is the +2 level intuition? The +2 level intuition is, I mean, if I can take out certain common term and the row operations do not change the outcome of the determinant of the matrix. Okay, so so what can we say about the first thing? The first thing is that row operations do not change the outcome of the determinant. That means if I operate this row with this row, I mean, like if we add, subtract, this type of operations, the typical row operations which you will be familiar with if you are familiar with the row reduced echelon forms and all those things. So this type of row operations do not change the outcome of the determinant if they are consistent. Okay, so yes, of course, if I just multiply a certain scalar, then the determinant will get changed by that scalar. But if we are consistent with the row operations that do not change the outcome of the determinant, that's the first thing. And the second thing is that product of the diagonals is the determinant of any upper triangular or lower triangular matrix. So this is lower triangular. Similarly, we have upper triangular. Okay, so that means what? if I have an upper triangular matrix, so this is the college level knowledge. Yeah, so it is kind of rhyming, but anyway. So if it is an upper triangular matrix, then the diagonal elements are precisely the eigenvalues. Okay, so hence if you take the product of the diagonal elements, you are bound to get the determinant of the matrix. So this is one of the important remarks that will be used. So it is that the diagonal entries of an upper or lower triangular matrix is are the eigenvalues of the matrix. Okay, so now how do we punch this first, second, and the remark? So let's first start with a 3x3 matrix. The pattern will actually follow. Okay, so if you can actually work out the 3x3 matrix part, the n cross n will actually be in the same pattern. Okay, so we will see the 3x3 part. So if you take a 3x3 matrix of this problem, so it practically looks like this. So here you have this, then S, R, S, 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 R. So now the first row operation that we are doing is so R1, R2, R3, these are the row 1, row 2, row 3. C1, C2, C3 becomes the column 1, column 2, column 3. Okay. So my new modified row 1, if I take this R1 plus R2 plus R3, so then what happens? So if I apply this operation on this matrix, then I get the matrix actually becomes like this: R plus 2s, R plus 2s, R plus 2s. These remains same. Okay. So now from the basic level of matrix multiplication, so the determinant of this matrix, and if I take the R plus 2s common, then the matrix that I have at hand is 1, 1, 1, S, R, S, 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 R. So all these three matrices have the same determinant. Okay, so computing the determinant of this matrix, so let me number it 1, because we are doing nothing but consistent row operations. So row or column operations do not do not change the outcome of the determinant. So if you have this, now let's work with this matrix. So the matrix now that we have is something like this: R plus 2s to 1, 1, 1, S, R, S, 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 R. Okay. So now as you can see that now my aim will be to make these two columns 0, because again we are same thing, that now consistent column operations do not hamper the determinant. So now if I choose this, my C1 prime is my C1 minus C2, and my C2 prime is my C2 minus C3. So what does this? What does these operations get me from this matrix? So applying these two operations, I have this 0, 0, 1. Then S minus R minus S, S, 0, R minus S, R. Okay. So now we have this. All right. Now if you look at it very closely, that you can see a pattern that basically is getting formed now. So what is that pattern? That I am actually eliminating two certain rows, and I am actually getting a matrix where there's only one multiplication, that is, I mean, there's only one column that we are worried about, because to understand the determinant of this matrix, it suffices if you take only the determinant of these column and row, right? So that means the minor that is getting that we are focusing on is this one. And as you can see that this is a very interesting minor, because this is a what it is. So this is an upper triangular matrix. So what happens if you do the same operation for 4 cross 4? Let us see, I mean, at least for our curiosity sake. So fine. So now as you can see here, that here the determinant will be, so it will be for 0, then minus 0, then plus 1 into S minus R into R minus S, right? So then here the determinant is becoming R plus 2S into S minus R into R minus S. Okay. So so these are, so this will be the determinant of the 3 cross 3. Now let's see what happens in the pattern of 4 cross 4. So in the 4 cross 4 you have this R, S, 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 so the first operation is exactly the same. So instead of R plus 2S, you are going to get here R plus 3S. Okay. And the moment you have this, then you have the matrix as 1, 1, 1, 1. Rest of the things are same. S, S, R, S. Okay. So now the same column operations will hold. So I will take C1. So if this is C1, C2, C3, C4, then I will take C1 minus C2, then I will do C2 minus C3, then I will do C3 minus C4. So what does that give me? So that gives me this R plus 3s into 0 s minus r 0 0, then you have 0 r minus s s minus r 0 0, then you have s minus s here, so it's 0, then r minus s, then s minus r, lastly you have 1 s s r. So this is the matrix that we have in our hand, right? So now you see that the same thing, the same pattern is practically following, right? Because the only column and row that we are worried about are these things. So the minor is this one. But what is the determinant of this? This is an upper triangular matrix. This is an upper triangular matrix. So the determinant of this will be s minus r into s minus r into s minus r cube. Okay. So see, here we have the same thing. Okay. So here we have the same thing, but we can. So will this be? Yeah. So it's minus r. I think I have, right. So it will be s minus r. S minus r. Sorry for that. So now, as you can see, that these will remain consistent in n cross n as well. So you can actually prove it by induction. So the induction argument is practically the same. So we have seen it for 3 and 4. So instead, whenever you are actually replacing 3 or 4 by n, then this becomes n minus 1. So if you take r plus n minus 1 is common, and then you are actually taking the column operations as c1 minus c2, c2 minus c3, c3 minus c4, like cn minus 1 minus cn. So then the last row, that the last column will only survive, and the minor will always look like this, an upper triangular matrix where each of the diagonal elements are s minus r, s minus r. Okay, so that's how you can actually compute the n cross n determinant. Now the only thing that you need to worry about is that, see, whenever we had 3 cross 3, then how did the determinant look like? Plus 0, minus 0, plus 1. But here it will be plus 0, minus 0, plus 0, minus 1. So now it will be r plus 3s into minus 1 into s minus r whole cube. Whereas for 3 cross 3 we had we had r plus 2s into s minus r whole square. So in generally what will happen is that in generally r plus n minus 1 into s minus r. So see, as you can see that it is 4 cross 4, thus this is s minus r whole cube. So if it is n cross n, then you will have s minus r whole to the power n minus 1. Okay, but there will be a sign change. So for 4 cross 4, so for 2 cross 2 we have minus, 3 cross 3 we have plus, 4 cross 4 we have minus again. So for n cross n, for n even and n odd, you just need to mention the sign. So let's call it plus minus depending on the even odd n. Okay, so now this is how you can actually, so see, this problem did not require too much of modern linear algebraic methods that we know as of now. It just required two simple facts, that consistent row and column operation do not hamper the outcome of the determinant, and the upper triangular or lower triangular matrices. I mean, if you take the product of the diagonal elements of upper or lower triangular matrices, then you are about to get the determinant. Okay, so that's the first question. I mean, the first algebra question from here. So the way we are actually covering is selected algebra problems. Then we will be going into the analysis stuff. later on we will make videos of each problems. Okay, so like each solution, then you can actually find it in our website. Okay. So fine, so this is what the first problem looks like. The second problem is a little bit trickier than the first one. Okay, so it's practically a ring theory problem, uh, which depends on the characteristic of the field. So let me see if there's any question. Just a second. Okay, so if it's books related for CSIR NBHM, uh, probably I will write some of the books down. You can check those. Okay, fine. So now let's see the second problem. All right. So the second problem is this question number 2. So question number 2 is let fx be the polynomial ring so over a field F over a field F. Prove that the rings. So prove that the rings fx modulo the ideal generated by x square and fx modulo ideal generated by x square minus 1 are isomorphic if and only if the characteristic of f is 2. So this is actually interesting. The characteristic is something that is that creates a lot of exceptional cases in the field theory, ring theory. Okay, so what it says is that, I mean, see, if it is not characteristic 2, then they are not isomorphic. So let me give you one of the examples like this. So I mean, let me kind of try to prove it like this, that since it is if and only if, what do we have is that if isomorphic, then characteristic 2. So we can actually take the contrapositive. So if not characteristic of f is 2, so if not 2, then not isomorphic. So what we are actually trying to show is that if characteristic of f is not equals to 2, then it's not an isomorphism. Okay. So if it is not equals to 2, it's a very simple observation. As you can see that x square minus 1, it's practically have two linear factors, x minus 1 into x plus 1, right? And if it is not characteristic 2, then minus 1 is not equals to plus 1. So what does characteristic of a field 2 means? It means 2 is practically 0 in the field F. So if 2 is 0, so if 2 is 0, then you have 1 equals to minus 1 in characteristic of F, if the characteristic of field is 2. But if it is not, then 1 is never equals to minus 1. Thus, these two are practically different ideals. Now, since it's since F is a field and these are basically principal ideals, so x square minus 1 having these two generators, the ideal generated by x square minus 1, it is contained in these two ideals generated by x minus 1 and generated by x plus 1, and these two ideals are maximal ideals in fx. Okay, because if you take fx modulo these ideals, you will get the it is isomorphic to the field f. Okay, so now the fact is that, but whereas the ideal x square, the only maximal ideal that contains x square is the ideal x. Okay, now we need to use a very, so now if you take ideal generated by x square, this is only contained in the ideal generated by x. Now we need to use this very important thing in the quotient ring setup, is that, I mean, here you can see that ideal generated by x square minus 1, these are the only two ideals that contains the ideal generated by x square minus 1, right? And similarly, ideal generated by x square is only contained in the ideal generated by x. Okay, so now what does that actually mean? So if I have a quotient ring, so given a quotient ring, so there is a bijection between the ideals containing I and I mean, if I have the set of ideals that contains I, there is a direct set theoretic bijection with the ideals of the quotient ring R mod I. Okay, so let's say, and since here I have a field, we can actually directly say it for commutative rings with unity as well. So set of ideals of R that contains I, there is a direct bijection, the set theoretic bijection, okay, with the set of ideals of R mod. Okay, so that means what? That means if fx modulo x square was isomorphic to fx modulo x square minus 1 when characteristic of f is not equals to 0, then the number of ideals has to be also same, right? The number of ideals, the number of ideals have to be the same if these are isomorphic. But here you can see clearly that the number of ideals of fx modulo x square minus 1 is 2. So here it has two ideals, that is the class of ideals, sorry, x minus 1 and the class of ideal x plus 1. Okay, so this is the quotient class. But whereas here it has only one ideal, the class of the quotient class of the ideal generated by x. Okay, so thus these are not isomorphic if characteristic of f is not equals to 2. Hence, by proving this contrapositive, we in turn prove our statement that if it is isomorphism, then characteristic of f is equals to 2. So now comes a little bit trickier part. So now what do we need to show? So now what we need to show is this, that uh, if characteristic of f is equals to 2, then it is an isomorphism. Okay, so this is something that we can directly prove by defining the uh, ring theoretic isomorphism. Okay, so So as you know that since characteristic of f is equals to 2, you have plus 1 equals to minus 1, since 2 is equals to 0. Okay, so what is characteristic of a ring? Characteristic of the ring is the smallest number which if you multiply with every element of the ring, you are going to get 0. So now since it's a field f, it contains the unity 1 as well. And if its characteristic is 2, then 2 into 1 is always 0. Thus 2 is 0, and hence we have this, that plus 1 is equals to minus 1. So what does this actually imply? It implies that x minus 1 is same as x plus 1. So if you take this ideal generated by x square minus 1, this is nothing but the ideal generated by x minus 1 whole square. Because see, this is what? This is your x minus 1 into x plus 1. But since it is characteristic 2, plus 1 is minus 1. Hence you have x minus 1 whole square. So instead of trying to find a group homomorphism from here to here, fx modulo x square to fx modulo x minus 1 whole square, sorry, x square minus 1, what we are basically going to give a homomorphism from x square to x minus 1 whole square, which is comparatively easy to show. Now every element here, how does they look like? So these elements are always of this form, right? Ax plus b plus ideal generated by x square, because everything of degree greater than or equals to 2, it belongs to the ideal generated by the x square, right? So thus every element of fx modulo x square, it is of this form ax plus b plus ideal generated by x square. So if I map this to a x, so a, just a sec, there is some, yeah. So then if I have a x minus 1 plus b plus x minus 1 whole square. So this is practically an isomorphism. See, why is that an isomorphism? If you want, you can actually try to prove that it is injective and surjective as well. It's pretty easy to prove that it is injective, because as you can see that if this belongs to x minus 1 whole square, then a and b has to be 0, right? Otherwise a linear, I mean, since it's an ideal generated by an element which has degree greater than or equals to 2, it cannot contain an element which has degree less than it, right? Less than 2. So ax minus 1 plus b belongs to this ideal only when a and b are both 0. And a and b are both 0 implies this is a trivial element. So the kernel is trivial. Okay, so I mean that's one way to prove that it is injective, right? That the kernel is trivial. So how are we actually proving it? We are proving that if this goes 0, which implies that this element is inside the ideal generated by this, that gives me that a and b, they are both 0, which in turn tells me this element is practically 0. And for every such element of this form, as you can see that these are the elements of fx modulo x minus 1 whole square as well. So these are the elements of these rings. So for each of these, I can actually choose x plus b. So it's surjective as well, since all the elements of here is practically looking like this. So it's both injective and surjective. Hence, it's an isomorphism. Okay. So the interesting fact here is that you can kind of try to understand it from a geometric point of view as well. So suppose let's just uh, assume for now that uh, what is fx modulo x square. Okay, and let's just assume that uh, in this characteristic 2 field we have an well defined situation of construct of roots of equations. Okay, because that's something. So fx modulo x square, this is nothing but the 0 point, and fx modulo x minus 1 whole square will be nothing but the point 1 in a line. So this is a point in a line, the 0th point. This is a point in the line that is the 1 point. Okay, so it's just a shift. So from here to here it's just a shift when it is of characteristic 2. If it is not, then it will not be an isomorphism that we have actually seen. Okay, so let's see. So this is the second problem. Let's see if there are any more questions. Fine. Okay, so now since we have passed the half hour mark and I am kind of going a little bit slower, so let's see the last problem from the group theory. It will not take much time to solve. So apart from this, there is one question from algebra, that is the question number 4, but it requires a little bit of computation. That's why we are avoiding it for now. We will see it in our upcoming videos. So question number 8. So it's a pretty interesting one. Question number 8 do not require a very vast conception on group theory. Okay, so maybe if you know silo, then it might help. But even if you do not know the silo theorems, you can actually solve it. The question number 8 of the subjective paper, it's this, that let G be a group having exactly 3 subgroups. Okay, so then prove that G is cyclic of order p square for some p prime. Now see, the first thing that you should understand here is that having exactly 3 subgroups, this is the twist in the problem. Apart from this, everything will follow. So what does that mean? It has exactly 3 subgroups. That means G has only one non-trivial subgroup H. Other than this, G, other than that, the only subgroups of G are the identity and G itself. Okay, so because of this, you can directly answer that G is not infinite. G has to be finite. Now, why so? Because if G is infinite, suppose let's say G is uh, infinite, then what you can do is you can actually take any element and generate subgroups with those elements. And since it is infinite, you are bound to get more than one non-trivial subgroups. Do you understand? So suppose let's say G is even countably infinite. Okay, let's say countably infinite. So then let's call it G is practically the set of GIs. All right, so I is natural number. So what you can do is you can take G1, you can take some GK as well, and there are bound to be disjoint subgroups as well, because if I mean sorry, not disjoint, I mean like different subgroups, at least one element is not there. Because since it's an infinite group, if after a certain point of time all the subgroups becomes equal, then you have a problem, right? Because then the infinity case is not, I mean, getting satisfied. And since it's given that it has exactly three subgroups, for any infinite group, you can at least find two non-identical subgroups if you just take any two elements and if you just generate it. It's just, I mean, it's kind of a very trivial thing. Okay, because if this is not true, then the G will not be infinite. Okay, fine. So it's finite. That's the first part that we know, that yeah, so it's finite. Now the first thing is that how are we going to say that it is cyclic of order p square? So the first thing is that how can we say that it is of order p square? So now that we have confined ourselves that G is finite, so what do we know? So we know that, so let's just take G to be n. So from the Silo's theorem, we know that if P is a prime that divides n, so this is a prime that divides n, such that P to the power r divides n and P to the power r plus 1 does not divide n, then for each of those P to the power I, so P to the power I from 1 to r, for each of these orders, you are bound to have a subgroup of that order of G. So that's what Silo's theorem tells us, right? But now look at here, it's pretty important that since there's only one non-trivial subgroup of G, there can only be one singular prime divisor of G. It cannot be, I mean, the order of G has to be p square. Why? Because suppose order of G is a composite number, let's just say like this n. So then this n, by the fundamental theorem of arithmetic, you can actually write it as product of pi alpha to the power I, the prime factorization. And for each of these pi alpha to the power I, you are bound to have a subgroup of that order. Okay, and that is why this exactly word is so important. They are not saying it is up to isomorphism. There are three subgroups. It's exactly three subgroups. Okay, so that is the reason that G has to be p to the power some k. But now it cannot be more than p square, because if it is more than p square for some prime, then again you are going to get p square up until p to the power k. All these orders, I mean, individually orders will have subgroup, I mean, of subgroups of this order. G will have subgroups of all these individual orders. Hence, the order of G has to be p square. So what have we accomplished from here? So what we accomplished from here is that first we showed that G has to be finite. Then we showed that G has to be order p square. Now comes the cyclic part. So if it is not cyclic, then suppose if it is not cyclic, so what does that mean? So since it is of order p square, you know that it has to be an abelian group, right? Because every group of order p square is abelian. That means what? That means there are, I mean, if you use the fundamental theorem, if you use the fundamental theorem of abelian groups, then there are two possibilities now that you have. So ZP square. Okay, so these are the two properties. But the moment you take ZP cross ZP, then you are establishing the fact that there exists two isomorphic subgroups of G. Since it is abelian, these are the only possibilities for the group G. That Zp cross Zp, G has to be isomorphic to either Zp cross Zp or Zp square. But the moment you take Zp cross Zp, then you are actually establishing the fact that there are two isomorphic subgroups of order P, which is not possible because it has only three subgroups. It has exactly three subgroups. Hence, the only possibility of G is Zp square. So the moment you have Zp square, you know that if G is isomorphic to Zp square, then it is cyclic. So there are many ways you can actually solve these problems, but this is the way I solve it. Okay, so you can also use the converse of the Lagrange theorem, the coset formulas. I mean, you can use it, but this is something that we can see from step by step. First, prove that the order is not infinite, then prove that the order is p square, then by the fundamental theorem of uh, finite abelian groups, you prove that it is isomorphic to Zp. Okay, so this is all that we solved. Three problems among the four subjective problems from the ISI M.Math subjective paper. So I will take in any questions that you guys have right now, and let's see if you have some questions. So I will be stop presenting. Okay. Yes. So Vijay, since I don't know if you are currently here, but anyway, MSc in 2019. Currently, I am preparing for fellowship exams, CSI and NBHM. Please suggest books for NBHM. Okay. So, if you are applying for the PhD programs, what you yes, good evening, Anupam, and good evening, sort of you as well. So, if you are preparing for NBHM for the PhD program, uh, then the books are the usual. Okay, so for topology, Moncrief, uh, the real analysis, part, Royden, Poland, for the basics, Bartlett Sherbert, and for the abstract algebra case, I think Damitfoot covers most of the things for the PhD entrance exams for NBHM. The linear algebra is the usual, whatever we have studied. Yeah, Terence Tao is also a very good book. Uh, so those are the basic books. So I mean, like, what we generally do in our preparation, which I have actually seen for some time now, even though I'm not that much experienced in the field of mathematics, I'm just in my third year of PhD. But what I have actually seen over the years is that, uh, being a pure mathematician, what we do is we mostly uh, follow the theoretical portions, but to clear competitive exams, you need to solve the questions to understand the theory. Okay, so this approach is much better. So whichever the books, there are books that are really good. I mean, for problem solving, you can actually for problem solving in real analysis, you can actually look for the Kaczor Nowak book. Okay, so that's really a good problem solving book. Okay, so uh, Ravi, I will come to you in just a second. And like, whenever you are doing maths, try to solve these problems. Okay, so for PhD especially, there are some things that are actually added with you, added in the syllabus as well, such as the complex analysis. Okay, the complex analysis, which I particularly preferred, is this. I studied from the Conway, and I solved Conway's exercises along with the Gamlin's exercises. Okay, so these kind of covers all the uh, necessary books that we can cover at the PhD level. But yes, of course, apart from that, there are various good books, and whichever suits you, you should read it. Okay. All right. So, what about differential algebraic geometry, complex analysis? Fine. Uh, in so if you are talking about books, then for differential geometry, I think the book by Docarmo is really good. So if you want to learn higher level differential geometry, then you need to understand the manifolds as well. So the manifolds you can study from John M. Lee, then the differential geometry part from uh, the Docarmo book. Okay, the algebraic geometry, there are two books that are, I mean, Hartshorne is uh, the best in the business, but if you are studying for the first time, Hartshorne might be a little bit difficult to catch on. Okay, so for algebraic geometry, you can read from Quinn Liu, and for differential geometry, uh, Docarmo, and the manifold part you can study from the John M. Lee book. Okay, so I think this kind of clears all the questions that I have at this moment. So I will pause for a moment and see if you guys have any other questions. Other than that, we'll meeting with I say objective question papers from the algebraic section in our upcoming videos. Okay, fine. So if nothing more to add, then thank you for attending my session, and hopefully the three problems that we have seen today, it might be helpful for your future endeavors as well. Okay then, thank you, and goodbye. Learn to enjoy mathematics. That's all I can say. Signing up.